Now Jordan Nicoules is going to talk about the stability of hair black holes with scalar Proca hair. He's a postdoc in the University of Aveiro. So, uh,
Thank you for the introduction, and thank you very much for uh, giving me the opportunity to talk today. It's my first time in Brazil, and it's a pleasure to be here. So, the work that I'm going to present has been done in collaboration with Carlos Egdeiro, Eugene Radu, and Miguel Zilão. And I must already put a disclaimer. So the work about hairy black holes with Proca hair is still in progress. So I won't give results about that today. And I will instead focus on the hairy black holes with scalar hair. But first, a bit of context. So I will go relatively quick on the context. I think it's just to stress that in the recent years we've had amazing developments in astrophysics and black holes physics, as we've also seen from the seminar this morning by Professor Genzo. And mostly two things: the detection of gravitational waves, first, with this plot that you've probably seen a million times, and the direct imaging of supermassive black holes by the Event Horizon Telescope collaboration. And some very generic questions that this discovery beg are these black holes actually black holes as we think of them? Are these Kerr black holes, or are these other kinds of objects? The broad context of this talk could also be what is the nature of dark matter, and I think we've had some also arguments from Dario this morning about dark matter. And a very, very broad question that I'm not trying to answer at all is what is the theory of gravity, and even maybe quantum gravity. But my point here is just to stress that often it's informative to look at a simple model, and from that we can learn some things. We can learn what are the underlying mechanisms, and I think that's basically what we try to do in physics. And of course, on the way, we can try to assess the astrophysical relevance of all of this. So in that case, the system that we're interested in is hairy black holes with scalar hair. And these involve a massive complex scalar field, which is minimally coupled to gravity with the following action. So I will take units with C and G equals 1. And we have to solve the Einstein's equations and the Klein-Gordon equation. Sorry, with the stress energy tensor that I've put here. And the solutions to these equations were presented by Herdeiro and Radu some 10 years ago in the following two papers here. And there is some data available on the website of the group. So for these solutions, we have a metric ansatz, which look like this. We use spherical coordinates. And this function n is 1 minus RH over r. And this RH will be the radius of the horizon. Now, we also have the scalar field ansatz that you can see here. And importantly, we have this harmonic dependence both in the angle phi and in time. And this is really this dependence that allows us to escape the no-hair theorems. And importantly also, it allows the stress energy tensor to remain independent of t and phi. So all these functions that you see in the ansatz, so this phi here, but also the functions f1, f2, f0, and w in the metric ansatz, they only depend on r and theta. So these solutions, they are regular on and outside the horizon. As I said, this horizon is located as r equals rh. In that case, they also have some symmetry along the equatorial plane, and they are asymptotically flat. And here, let's have a look at the parameter space for these solutions. So once you fix the mass mu, and we will take it as 1 for the numerics, then you have 4 parameters to describe these solutions. First, the number of nodes n, and we will take it as 0. Then the azimuthal number m, and in our case, we'll take it as 1. And you have then 2 continuous parameters, omega and RH, and you can see on this plot, so this is for n equals 0 and n equals 0 and m equals 1. This is actually represented in terms of the mass on the y-axis of the whole system and the frequency omega on the x-axis. And the region of existence of these hairy black holes is a blue shaded area. And it intersects the region where Kerr black holes can exist in that part here of the parameter space. It is delimited by this line, which is the existence line, which corresponds to the Kerr black hole, but with a weak scalar field around it, a scalar cloud. And it is also circled by this red line, which is the boson star limit. So there the horizon radius vanishes. And another important fact is that the scalar field has to obey what we call the synchronization condition. So this is this condition here, omega is equals to m times omega h, and omega h is the angular velocity of the horizon. And this is actually the value of the function w that you could see previously in the ansatz, taken on the horizon of the black hole. And as stressed yesterday by Carlos, this is also related to this onset of superradiance. So if you remember from his talk. So the main question that we want to answer in that work is, are these stationary? So yeah, I failed to mention that. So the space-time is stationary and axisymmetric, even though the scalar field has some time and angular dependence. So the question is this system actually stationary? Does it remain as it is, or does it evolve to another stage? And what is this other stage if it's the case? Is it to Kerr black hole? Is it to another hairy black hole in this parameter space? And the answer actually to that question may depend on where we are in the parameter space. Because for instance, where these black holes coexist with Kerr, they have been shown to be entropically favored. But we know also from previous works by Sanchez-Gual and collaborators that for the spinning boson stars, scalar boson stars, these are unstable and they suffer from non-axisymmetric instabilities. So in that region of the parameter space close to the boson star limit, what happens? So to answer that question, we'll perform full 3D numerical simulations. And as I mentioned in the very beginning, so far we have only results for the scalar case, but it's work in progress to test Kerr black holes with a Proca hair, which is a similar system, but instead of a scalar boson, you have a vector boson. And in that case, the rotating Proca stars are stable. So we want to see if it changes anything in the hairy black hole case. Now, regarding numerical evolutions, we use the Einstein toolkit. This is an open source and a widely used numerical suite to perform these evolutions. It includes a wide array of utilities like Horizon Finder, the evolution code itself, some analysis tools, and so on. And it relies on finite differences on a Cartesian grid, has mesh refinement, and is efficiently parallelized. I also briefly want to mention that we rely on the BSSN system for the evolution. It involves the 3+1 formalism that was also mentioned by Jose yesterday. But the only thing that you need to remember from this is that it's a way to recast the Einstein's equation as a Cauchy problem, so an evolution problem, so that we can speak really about time evolution. We separate time and space again, and we look at results on slices. The other point I want to stress before showing to you the results is that we are not using the ansatz for the metric as it is. We have to do a coordinate transformation, and this coordinate transformation allows us to have sort of a copy of this metric, but inside of the black hole. This makes use of quasi-isotropic coordinates. And this introduces a puncture at the origin. And we'll use this puncture in the rest of the work, and you can think of it more or less as the center of the black hole in our case. So now let me show you the results for this. So these are preliminary results. And I will be focusing on two physical systems in the two regions of the parameter space that I've mentioned before. So a first system, which is in this region here, where Kerr black holes can exist. And another one here, which is close to the boson star limit. So this I will refer to as the very hairy black hole. Some parameters about these solutions. So again, they have the no nodes and m equals 1. The frequencies you can see here, the horizon radius as well. The horizon radius is a coordinate-dependent quantity, so it's a bit different in our simulations, but not that much. What is important here is just to remind that the mass of the black hole in the first case is around 75% of the total mass, while in the second system, it's just around 10%. So, for the first system, we actually see no instability on very long time scales. So here it's just a zoom on the beginning of the simulation to show you the oscillations of the real part of the scalar field. And the blue curve and dots are the numerical results, and the orange curve is the analytic expression that we expect. And this goes on for longer times than what I'm showing. Also, if we look at the scalar field energy over the course of our simulation, so now see that the time goes from 0 to 1,000 in the units of 1 over mu, then the difference between the initial value and the final value is less than 1%. Another indicator that the thing is pretty stable is by looking at the scalar field deformation in the equatorial plane. So we look at the quadrupole and compute these two coefficients, eta plus and eta cross. And you can see that they stay of order 10 to the minus 13, 10 to the minus 12 over the course of the simulation. You will see that in the other system it will be dramatically different. We have a little bit of gravitational waves at the beginning of the simulation, but really it's probably just the junk radiation from the numerical initial data. Because when we look at the values of the energy, it is of order 10 to the minus 8, and the total mass of the system was order 10 to the minus 1. And it's the same for the angular momentum carried away by these gravitational waves. So the bottom line here is that for this system, I mean, I could show you plots that are basically just lines, which is a bit boring. But this hairy black hole is stable actually on long time scales. And whether you consider the scales of 1 over mu, the scales of m, or the scale of 2 pi over omega. There are other indicators that I'm not showing here that this system is stable. And we obtained similar results for another hairy black hole in this region of the parameter space. So now we get to the more interesting case, I think, where at least the plots will be a bit more interesting. So this second system here, again, has most of the mass in the scalar field. And what we see, the main result of these simulations is that we can see the black hole starting to move in an out spiral movement. And this out spiral is in the direction of the angular momentum. And for these scalar boson stars, the density has a toroidal shape. And when the black hole gets to the regions where the density is higher, then it starts to accrete the scalar field. And again, simulations with another system in this region of the parameter space show the same behavior. So first, I was talking about the movement of the black hole. This is a plot that shows it. So you have the coordinates of the puncture I was mentioning before. X and Y are these two curves, and Z is this one. So in the simulation, we actually impose symmetry against the equatorial plane, but relaxing this symmetry did not lead to a dramatic change. The movement of the black hole was stable in that direction. But this is really like the exponential out spiral that I was mentioning. And you can see it here in the XY plane. So I have an animation about that. I will show it a bit afterwards. I will adapt how much videos I can show you depending on the time I have left. But basically the black hole then starts spiraling out like this. And eventually it reaches the regions with higher scalar field density. And then due to the interactions with the densities and probably the numerical noise that starts it all, it starts to drift a little bit. Now this begs the question, what happens in the stable case, actually? And if you look at the puncture position in the stable case, it looks like that. And you can see that the XY position, although there's a bit of movement, it's nothing like the exponential we were seeing before. And it stays at very low values. If you look at the trajectory in the XY plane, it's also pretty much erratic. There's not this structure of out spiral in the direction of the angular momentum. So this is another indication that this first system is actually stable. So a few remarks before showing more results. Actually, we need to track the puncture with the toolkit. If you don't track it, it's possible to do it, but if you don't, then the code just crashes. And also tweaking the numerics, like changing the place of the boundary, changing the refinement levels that you have, or even correcting some small bugs in the code, they result in a different exact trajectory, but the trend is always the same, and you keep this exponential out spiral with the same slope and the same angular frequency. So I was mentioning that the scalar field was accreted, and you can see it clearly from this graph. So in blue you have the energy in the scalar field, and in orange the energy in the horizon. And you can see that there's very dynamical phase here between around 700 and 1,500, where most of the mass in the scalar field goes into the black hole. And by the end of the simulation, which here we stop at 2,500 in the units of time, then there's only around 5% of the energy left in the scalar field. And overall, so here, everything is relative to the sum of these two components at the initial time, but remember it was over the one anyway. So the mass at the end is around 95%. So there is a little bit of a loss, but this could also be expected for numerics. Angular momentum, we can see the same kind of trend. Here, there is more of a loss. Also keep in mind that these scalar field energy and angular momentum, they are computed as Komar integrals, which makes sense when you have axis symmetry or stationarity, which we clearly don't have anymore. So this is more of an indication. But you can see the exchange between the scalar field and the black hole. And at the end of the simulation, actually, the black hole is more spinning than it was at the beginning, which you can see from the dimensionless spin here. Regarding gravitational waves, there is a bit of emission again. So this time I'm focusing on the very dynamical part between 700 and 1,500. So you have a bit of emission of gravitational waves during this time. Most of it in the 2-2 mode, and 2-2 actually, which is the same as 2-2 here. But again, the total number is of order 10 to the minus 4 to be compared to order 1. So it's relatively negligible. Angular momentum seems a bit less negligible. It's of order 10 to the minus 2, but it cannot explain the difference that we are seeing in the other graph. Also, of course, these are approximations because we have to extract these at a finite radius. Now, I was saying that the scalar field deformation was significantly different in that case. You can see that here. So first, we still have this phase where nothing really happens, but then the scalar field is getting deformed exponentially as well. We've tried to add an initial perturbation on the scalar field, and what happens is that actually you would have your perturbation like that, but at that same stage it would start increasing exponentially, which means that this movement of the black hole is really the driving phenomenon around this instability. It's not due to the perturbations in the scalar field. And finally, before showing some movies, I want to mention that when you look at the structure of the scalar field, so this is the real part of it, you will see different features along the evolution. So when we start, we have this m=1 structure here, but after the evolution and after the black hole starts to disrupt the scalar field, we actually see some patterns which are more like m=2. I don't know if you can really see, but you can also come and see me. I'm happy to show you directly on the computer. The black hole has really increased in size due to the accretion. And at late times, it even has m=3 structure. Okay, so I will show some movies, not all, so feel free to come later to see more. But first, let me show you this trajectory of the black hole. So this is the out spiral movement that I was mentioning. So, well, basically it stays like this until it reaches larger scales. So I will skip the rest. I will show you the density. So this is the part with higher density of the scalar field here in yellow. And eventually you will see that the black hole will move and accrete the scalar field. Okay, I went a bit too far. Should have been patient. like that. And finally, the other thing I want to point out is with the linear momentum. So here, blue is negative and red is positive. So this is the momentum of the along the. So this is the xy plane, and this is the x component of the linear momentum. And in the initial configuration, so this part in blue goes like that, and this part in red goes like that. And this is what you expect from something that is rotating like this. But during the evolution, what we see when it becomes very dynamical, like that, is that actually, so here red again is positive and blue is negative. So you can also really see the accretion from that. The scalar field is going like that and like that. So let me go back to the presentation. Again, I'm happy to show more of these movies if you want. So the interpretation of this that was mentioned yesterday is that in the case of the very hairy black hole, actually the black hole is kind of a test particle in the scalar field, gravitational field, for which the origin is an unstable point. So the numerical instabilities are enough to trigger this movement of the black hole, and then it just gets amplified until the point where the black hole will reach the scalar field and accrete it. So as I mentioned, on the other hand, it's stable against the Z perturbations. And also, if you put a scalar field or metric perturbation on top, this will remain the driving mechanism in the evolution. So I'm already running a bit out of time, so let me jump to the conclusions and prospects. So again, the main result is that in the region of the parameter space where these black holes coexist with Kerr black holes, we see that they are stable. In the very hairy black hole case, we can see that there is this instability and the scalar field gets accreted. It's hard in that case to know the exact end state, whether it's Kerr, whether it's kind of migrating to another hairy black hole, also because of time scales and limitations by the numerics. But it's also it's still very interesting to see this behavior. So the current work is on the Proca star, hairy black hole with Proca hair. And since the spinning Proca stars are supposed to be stable, how does that transfer to the hairy black holes in that case? Also, while for the scalar case, the density has a toroidal profile, in the Proca case, it's more spherical, so this should play a role in stability of the origin. So stay tuned for more on this. And finally, for future work, then there are many avenues. We can try to explore more in depth the parameter space to see if there's a transition between these different behaviors. Also test more exotic configurations. We can have a look at situations where the total angular momentum, dimensionless angular momentum is bigger than 1. We can look at exacted states or other M's. So a lot of things to do still. So here are some acknowledgements. And with that, I thank you, and I will hypnotize you for the questions.
Thank you, Jordan, for this really nice talk. We have a few minutes for questions. Any questions? I have a couple of questions myself, so I should start. So what's relevant when you were showing the movement of the puncture, that's gauge dependent? And I know that, for example, it's really well known that BSSN drifts the black hole out of the equilibrium, if you want. But there are another formulations like C4, for example, that somehow eliminate this kind of behavior. Do you think that this is a physical effect? If it's a physical effect, why we are seeing this drifting?
Thank you for the question. So, for sure, it's depending on the gauge. I think that the movement of the black hole. Regarding the formulation, I'm not sure. But something I was thinking about is, in the past, I've tried to implement an evolution code which was in spherical coordinates. And for this case, then the symmetry, like the phi symmetry, would be better satisfied. Nevertheless, I think that if you had a perturbation on top, maybe you wouldn't see the black hole moving, but you would still see the scalar field being accreted. So, so the exact, the fact that the black hole moves, I guess you could always try to put yourself back in the frame of the black hole. But here, since most of the mass is in the scalar field, does that make more sense? Kind of. Also, numerically, it's straightforward to do it like this. To try.
For example, if this is an artifact of the formulation, I'm wondering if the accretion is changing because of that. Because this is an artifact of the formulation. For example, if you move to another formulation that C4, for example, maybe the system is more stable or not. I'm not sure. So, any comments on that?
Well, I don't have a guess, but it's an interesting question. I will think of it.
It's kind of weird.
Is this on? Yeah, it's on. So thank you very much, Jordan. My question is not very deep. I was just curious because this initial kind of the puncture motion, the initial part at least, is very smooth, and since in the very early stages you probably can use some kind of time-like geodesic approximation, I was wondering if you could actually make some kind of analytical calculation that could describe this initial part. That would be nice, especially because, well, it seems a very irregular pattern, and what's the mass fraction until after which well, this approximation is no longer valid. Do you have any comments on this?
I think it would be interesting indeed. Probably in the beginning of the trajectory, it should be valid. So, at least to some extent. I mean, so I was saying also that this is a very hairy black hole, but we have configurations with even more hair, for which probably it would even be even better suited. So maybe in these cases we could check it even better. Yeah, this is a good idea. I think we could try to see what to do with it.
Any more questions?
Thank you very much for the talk. I'm wondering if we could explain in the last slide that you presented, the slide where you were thinking, where you're, yeah, this. There appears a m equal 3 mode, right? There is an explanation why it's migrating from m equal to 2 to 3 in this case.
So something that has been suggested to us and that I would like to try to check if we can somehow try to define the angular velocity of the horizon at that stage, like if we can approximate it with care, for instance, since the scalar field is low, and see if it's close to the synchronization condition or not. So this is more speculation. This is at the stage of an idea, but that could be the thing. But something that I've noticed in the evolution, so maybe I can try to show it to you on the movie, is that actually even when it's m equals 2, it's not very clean. So you already can see further away from the black hole some m equals 3 pattern. So let me try to show that to you. I don't know if you can see it well there. But close to the black hole, it's still kind of m equals 2. But if you look further away, you still already have this m equals 3 like pattern. So this one appears pretty soon, but it kind of just gets to the black hole later than this m equals 2. And here it's just also a truncation of the whole computational domain. Further away, it's hard. I mean, just by eye, there's no real structure. So it's very low values of the field and.
This case was for the case when the black hole is at the spark, right?
Yes. Yes.
So you think that this behavior of appearing then equal to m equal 3 is due to the black hole or due to the scalar field structure? Because I think if you migrate to m equal 2 to m equal 3, I think could be the presence of the black hole which is causing the migration, right?
Well, if it's somehow kind of synchronized, then I would say yes. Also, the black hole is really a perturbation in the field, so when it starts to like really to be dynamical, it's really disrupting. So at some point, you don't really have even structure. So I think this is then when the black hole increases in mass and angular momentum, or then somehow it reaches a state that is more that is closer to this synchronization.
You showed plot when the deformability or deformation in the x and the y deformation was increasing exponentially. I think you passed it. I think that. Could you repeat why the exponential growth stops and then saturates? Because I heard that you mentioned something like that, but
No, I don't really mention that. Well, one thing here is that at that stage there's not much of scalar field anymore also. So if you look at the times, it's so this is really the period where a lot of things happen, but afterwards there's not really any scalar field. I mean, there is some scalar field left, but it has been perturbed a lot by the black hole, especially if you take the whole numerical domain into account. So I think that this first phase is really the impact of the black hole starting to move. It interacts with the scalar field. Also, even without black hole, if you look at the boson star, the spinning boson star, when it has these non-axisymmetric instabilities, it will kind of make two components. If you remember yesterday in Carlos' talk, the movie also, we could see that it makes two components before collapsing to the black hole. And this would manifest in this kind of way as well. What I was saying earlier is that if you put at the initial time some perturbation in the scalar field, it will, for instance, something of order 10 to the minus 4, 10 to the minus 5, you would see here this kind of behavior, like say a straight line in the log plot, until that exact time when you will see the rest of the exponential. Because the black hole is already moving around, and this is what causes eventually the thing to blow out. This was my point earlier. Thank you.
All right, so let's thank Jordan once again.